Hello everyone, welcome to my channel. This is my part 2 adsorption isotherm video. In my part 1 video, I tell you what is the adsorption isotherm and why we use adsorption isotherm, different types of adsorption isotherm, and I describe what is French-Lis isotherm, what is Langmuir isotherm, and the link of this previous video, that is adsorption isotherm part 1 video, is in the description box. You can see it by click on the link, and in this video I will show you what is the Langmuir isotherm equation for n atomic gas. In my previous video I show you what is the Langmuir isotherm equation for monoatomic gas. In this video I will tell you what is the Langmuir isotherm equation for n atomic gas, and what is the Bate isotherm equation, and what are the limitations of Langmuir isotherm, and when we can use the Bate isotherm, etc. This topic, that is the adsorption isotherm topic, is very important for competitive exam like NET and GATE. There is at least one question which is from adsorption isotherm topic. Please see the full video, and please comment on it, how to improve my teaching skill. Please see the full video. Thank you. Now, Langmuir isotherm for diatomic or polyatomic gas, that is n atomic gas, is different from the isotherm equation is different from the isotherm equation of the monoatomic gas. Just see the derivation of the Langmuir isotherm equation for n atomic gas, which is more generalized from. If n is equal to 1, if you put n is equal to 1, this is for monoatomic gas, and for n is equal to 2 for diatomic gas, and so on. Now, let's this is the actually this is the dissociative mechanism. And let assume the yn is the n atomic gas. If the n is equal to 1, it is monoatomic gas, for 2 and for diatomic gas, and so on. This yn gas is adsorbed on the adsorbent S, and it will form SY. For n atomic gas, the number of adsorption site is required is n, and this n atomic gas at first dissociate to ny, and then this ny form the n number of adsorbed y. This sy means y adsorbed on the surface S. S is the surface, yn is the n atomic gas molecule. Now Ka is the rate constant for forward reaction, that is the rate constant for adsorption, and Kd is the rate constant for backward reaction, that is rate constant for desorption reaction. Forward reaction is adsorption reaction, and backward reaction is desorption reaction. In my previous video I show you everything about the forward reaction and backward reaction and the Langmuir isotherm for monoatomic gas. Now, if the pressure of the gas molecule is P and theta is the fraction of the surface occupied by the gas molecule, then 1 minus theta is the available fraction of surface for the another gas molecule to occupy. This is the 1 minus theta, and theta is the fraction of gas molecule, fraction of surface adsorbed by the gas molecule. This is at time t, not at time t0, that is when adsorption is not occur. This is at time t, when adsorption when during some time adsorption takes place. And here you must be kept in mind that the adsorption is the monolayer adsorption for Langmuir Isotherm equation. Now P is the pressure of the yn gas molecules, 1 minus theta is the available space, and theta is the fraction of a surface occupied by the gas molecule. Now and at equilibrium the rate of adsorption is equal to rate of desorption. Now for that the forward rate for forward equation, rate equation is equal to K into concentration of Yn into concentration of S to the power n. That means concentration of Yn means, as it is a gas molecule, then concentration of Yn is equal to the pressure of the gas molecule, that is Ka into P, and this is the S is equal to 1 minus theta and 1 minus theta to the power n, that is the forward reaction rate is equal to Kp into theta to 1 minus theta to the power n. And the backward reaction rate equation will be Kd into concentration of S minus Sy, not this is not S minus Y, this is Sy, means adsorbed gas molecule, concentration of adsorbed gas molecule to the power n, that is theta to the power n. And at equilibrium these two rate equations are equal, that is Ka into P into 1 minus theta to the power n is equal to Kd into theta to the power n. Now if you rearrange this equation, you can get that theta is equal to 1 theta is equal to Kp to the power 1 by n divided by 1 plus Kp to the power 1 by n. By rearranging this equation you can get that theta is equal to, that is the fraction of the surface occupied by the gas molecules, is equal to Kp to the power 1 by n divided by 1 plus Kp to the power 1 by n, where K is equal to Ka by Kd. K is equal to Ka by Kd. And this is the generalized form for the Langmuir Isotherm equation. If you put n is equal to 1, then you can get the equation for the monoatomic gas, that is theta is equal to Kp divided by 1 plus Kp. And for n atomic gas, for dissociative mechanism n atomic gas, you can get that theta is equal to Kp to the power 1 by n divided by 1 plus Kp to the power 1 by n. This is the Langmuir adsorption isotherm for n atomic gas. Now there is some limitation in case of Langmuir isotherm. In my previous video I told you what are the assumptions for the Langmuir isotherm equation, and these 5 assumptions. These 5 assumptions are the assumption for getting the equation of Langmuir isotherm. In my previous video I clearly explained all these assumptions. Now the first two assumption, that is the this adsorption is the monolayer adsorption and there is no interaction between the adsorbed molecules. This assumption the monolayer adsorption and there is no interaction between the adsorbed molecule, this assumption is holds when the pressure of the gas is low and the temperature is the moderately high temperature. At high temperature the adsorbed molecules overcomes the attraction between the adsorbed and unadsorbed molecules, but in case of low temperature this assumption is not applicable, and at high pressure the monolayer formation is not occur. At high pressure the multilayer formation is occurred. Hence these two assumptions for Langmuir isotherm, at first we have to assume there are 5 assumptions for Langmuir isotherm, and these two assumptions is applicable when in other words Langmuir isotherm is applicable when the pressure is low pressure and the temperature is moderately high temperature. But at high pressure and low temperature Langmuir isotherm is not applicable. In that case there is another isotherm, that is Bate isotherm. Actually, adsorption isotherm, this isotherm is interpreted by the three scientists. They are Brunner, Emmett and Taylor. And this bait isotherm is mainly when we cannot apply the Langmuir isotherm equation, that is there is multilayer formation occur and the temperature is not so high, or temperature is low and the pressure is high. In that case there are multilayer formation occur and then we have to take help of bait isotherm. That is, at high pressure and low temperature Langmuir isotherm is not applicable, and in that case multilayer formation occur, then bait isotherm is comes. Now the equation for the bait isotherm is equal to I am not showing the derivation of the bait isotherm. You don't need to know the derivation. If you know the final expression of the bait isotherm, you can easily solve out the problem which is in the NET or GATE examination. So the final equation is that P by V total into P0 minus P is equal to 1 by V mono into C plus C minus 1 divided by V mono into C into P by P0. I will tell you what are the significance of the P, V total, P0, V mono and C. Now this is the equation for the Langmuir bait adsorption isotherm. For Langmuir isotherm the equation was theta is equal to Kp by 1 by Kp, or you can replace the theta by V mono, and this is the and this is the equation of the bait adsorption isotherm. This is the equation of the bait adsorption isotherm. This is a complicated equation compared to the Langmuir adsorption isotherm. Now P is the P0 is the pressure at time 0, that is when the first layer formation is occur, and V total is the volume of volume of the total adsorbed gas molecule. V total is the volume of the total adsorbed gas molecule, and V mono is the volume required for the monolayer adsorption. For the monolayer adsorption, V mono is equal to monolayer adsorption volume, and C is the K1 by KL. Now what is K1 and what is KL? For bait isotherm the multilayer formation occur, that is this G stands for gas which is adsorbate and S is the adsorbent. Then G plus S at first form GS, then G again GS, it is from G to S, then again G to S, G3S, like that. This process occur up to the n minus 1, that is if the gas molecules are Gn, then up to the there will be the n gas molecule. If there is n G gas molecule is available for the adsorption, then the G plus Gn minus 1 into S will be Gn into S. This is actually the multilayer adsorption process. For the monolayer adsorption process, this will be the equation G plus S is equal to G plus S to Gs. This is the adsorbed gas molecule. Now the rate constant for the first reaction, that is when the monolayer formation occur, the rate constant of the first reaction is equal to K1. The rate constant of the first reaction is equal to K1, and KL is the rate constant of the rest of the equations. KL is the rate constant of the rest of the equation. Now why we take or why it is considered as the rate constant of all other equation rather than first equation is taken as same, that is equal to KL. This is because the and this is because the interaction between the adsorbate and adsorbent, that is the gas molecule and the adsorbent surface, decreases very rapidly as the distance from the surface is increased. That is when monolayer formation occur. Then for the bilayer, for trilayer formation occur, or and so on, the interaction between the adsorbed bait and the adsorbent is decreases, and for that reason the for rest of the reaction, that is if we take as the K2, K3, K4 and so on, then the difference between K2, K3 or K3, K4 or K2, K4, this difference is very low, or it is comparable at the adsorption of the after the monolayer formation. The interaction between the adsorbate and adsorbent decreases, but the K1 varies rapidly. K1 has very large value compared to KL. K1 has very large value compared to KL. That's why the rest of the equation, rather than first equation, the rate constant is same, and which is equal to KL. And here another interesting fact is that KL is actually the equilibrium constant corresponding to the saturated vapor liquid equilibrium. The saturated vapor liquid equilibrium, this is the KL actually is the equilibrium constant of the saturated vapor liquid equilibrium, and C is equal to K1 by KL. K1 by KL. This is the bait adsorption isotherm, where Langmuir isotherm equation is not applicable because of the multilayer formation, and the condition is the high pressure and low temperature condition. Then you have to use this multilayer formation this multilayer formation concept, and you have to use the bait isotherm equation for solving out the problem. And if you remember only the equation, then you can solve out the problem easily, and the meaning of the each term involved in the equation. In my previous video, I told you what is the French's isotherm and what is the Langmuir isotherm for monoatomic gas. In this video, and this is the second part of the adsorption video. In this video, I told you what is the Langmuir isotherm equation for the n-atomic gas and what is the bait isotherm equation. Actually, there are these three equations which are important for our exam purpose, that is French's, Langmuir and bait isotherm. You have to remember all these three, but for bait isotherm you don't need to know what is the derivation of the bait isotherm equation. Now thank you for watching. If you like my video, please subscribe my channel, and thank you again. Thank you.